Dr. Barth?
Sir.
I just need to get an audio check for you.
Okay. 7 years ago, our forefathers brought forth on this nation, etc., etc. So there we are. I can give you more. Once upon a midnight weary, as I pondered bleak and dreary. Good deal. I posted the announcement of the book today on a number of groups in Facebook, and I'm getting lots of responses. So I'm just answering some questions.
You guys hear me?
I can hear you.
Now, do you hear me when I'm in my office?
I was not hearing anything, no.
Okay. All right. Did you hear anything?
I didn't hear you talking, but I am getting an audio signal.
Yeah, I see my microphone working. So.
Yeah, try again, I guess.
Okay.
I see it. I see a signal, but I didn't hear you. All right, I got you, Scott.
How about now? Hello?
Yes.
Hello?
Yes.
Yes.
You do hear me?
Yes.
Yes.
All right. I hear an echo from you.
Right.
Right.
Right. Right. Okay. Okay.
That's why I'm going to kill my mic.
Kill my mic.
All right. What does Daniel sound like?
Dr. Barth?
Dr. Barth?
Sir?
Okay. I hear you now.
Scott over there?
You hear
I
me all
cannot.
right,
I have
Daniel?
No audio?
I hear your voice, but I have nothing coming over the laptop or anything else right now. I'll scoot aside and let you fiddle.
It was just it was just turning.
Oh, okay.
You don't want to get it too loud.
Are we already streaming?
I hear Scott now.
This is so cool. Hello, everybody. This is Scott Roberts and Dr. Daniel Barth here for the 51st episode of How Do You Know, where Daniel will be talking about Planetary Nebula. And from what I understand, there's another momentous moment. Is that right? Momentous moment?
There is another momentous moment.
Right now, I think that Joe Biden is about to release or talk about the first images from the James Webb Space Telescope. If you are so inclined, you could watch our show and watch his show as well. I did actually put a link into NASA's website for their multimedia stuff. So that should
good. Space.com is going to feature it as well. I'm sure it'll be all over the web, and it'll be on
it's going to be
YouTube and everything.
It's a world event. Yeah.
It's a world event.
Yeah, we're very happy as well. But you know, we can do two things at once here, I think. So, but
yes,
you know, and I didn't have the rights, you know, the NASA rights to restream it. So, you know, myself.
No, and this happened just very quickly, Scott. It's been a really fun week at the Barth Land Ranch out high atop Round Mountain here in the Ozarks. Yep. I got a call last Friday from Joe Palca from NPR, their science consultant. Hi, can I interview you about the James Webb Telescope? And I'm like, wow, sure. You know, the first question that comes into my head, this guy is obviously swings a big bat in media. I'm like, gee, you could pick anybody. Me? Golly, thanks. That's awesome. And he said, yeah, he had found me through Astronomy for Educators. And he said, I want somebody who regularly teaches people how these things work rather than a physicist or an astronomer who is used to talking at people at the graduate level. And then he called this morning and adjusted the time. He said, by the way, the president has messed up my schedule because he's just now decided that he's going to release this image himself and talk about it as a national TV event. I'm like, really? Wow. And so we chatted together for about 20 minutes, half an hour about Planetary Nebula. And of course, our audience here is going to get the bigger, better, deeper, richer, more textured discussion of Planetary Nebula.
Right.
So that will be exciting. And I hope you'll check out NPR. And I'm not sure what program they're going to release it on. He said he's going to be using parts of the interview, and we'll see. But it will be fascinating. And I'll try to find out where it's going to be broadcast by him, and I'll release a link to Scott so you all can find it.
Yeah.
That will be exciting.
Cool. Very cool.
Yeah.
Right.
And
so your topic today is Planetary Nebula, and I happen to really like Planetary Nebula. Okay, for a couple of reasons. I mean, they're intricate. They tell us a story about stellar evolution. They're beautiful. To me, it's like
They are.
seeing all these different kinds of blossoming flowers, and
And they have a deep and rich history in astronomy. And we like to do that here on this show.
yes,
We like to
right.
dive into the history of discovery and all the twists and turns. And Planetary Nebula have a very rich history. It goes back hundreds of years. And like so many things in astronomy, we're stuck with a name. It's not really descriptive or accurate, but it's historically familiar. And I guess when you've been using a name for a few hundred years, people just like to stick with it.
Sure.
So
Right.
that's fun. And we had another exciting event, Scott, and the Star Mentor book.
Right.
And this is hands-on projects and lessons in observational astronomy for beginners. And this is the book we've been talking about for months, literally. And it's been considerably more, been almost 2 years in the writing and publishing. And it represents 45 years of experience in terms of my career in teaching astronomy. And what we've realized, Scott, and you and I know this, a telescope is a party in a box. You set your telescope up in your driveway, looking at the moon, Saturn, whatever, and immediately you have people will literally drive past you on the street and pull their car over and get out. Is that a telescope? Can I ask you just one question? Can I have a look? And a lot of people are like, well, I'd love to help these folks who come over, but how do I do that? This is for you. I wrote this for you. There are also, as Scott and I have discussed many times, millions of new telescope and binocular owners, courtesy of COVID. We were stuck in our houses. What do we do? Oh, let's go look at the sky, which is great.
You need
and
this book.
We love you all.
That's right. You need this book.
We're glad you're here.
Teachers need it.
That's right. And
if you're an astronomy
parents, I've had contact.
guy, you need it. So
that's right. There are people sometimes say, "Oh, how can I use this book if is it all just text?" No, guys, there's something like 180 illustrations in this book. Many are in full color. Most of them are drawn by yours truly. So if you're a long-term fan of the show, you know my skills or lack thereof in illustration. But I've been drawing diagrams and helping students learn for nigh on to half a century now. And so lots of these illustrations in here. And my editor, like, really? You want another picture of that? You want another illustration of that? And yes, I do. Because I've seen how books like this are used in classrooms and by individuals. And people are like, oh my God, if you've ever got a set of instructions to put together a gas barbecue or an IKEA desk, you're like, geez, can't you just give me a little bit more detail? And so I've really stuffed this with detail to help. And it's available right now on Amazon.com. It's also available at Springer.com. And I don't know, maybe Scott will be selling it. I don't know if you guys do books at all.
I think it's a great book. I think that
there you go.
A lot of the stuff that you showed on How Do You Know, you guys might recognize these. Okay.
Yes. How Do You Know fans there's a lot of new material that's never been on How Do You Know. But if you're a How Do You Know fan, then you will see familiar things in a nice format where you can open it up. And I think this really, Scott, I'm really hoping that it helps people plan their observing. And I was talking to Kent about this earlier, and Scott knows this just as well as I do. There's a kind of fatigue, and it's not just astronomy, it's anything. You get a new thing. Ooh, I'm going to play tennis. I'm going to play golf. I'm going to get a telescope and do astronomy. And after you've done it for a couple of weeks, and then you're like, but what's next? What do I do with it now? Is this all there is, as the old song says? And this is designed to combat that. This takes you through tracking the telescope, setting it up, learning to find the sky, reading a star map, learning how to find things, learning how to guide your scope, learning how to do new things with your telescope. And we've mentioned it many times in this program, the more knowledge you bring to the eyepiece, the more value you take away from your observing experience. And this is designed to give you all that information, that knowledge, so that when you go out, you're not going to say, oh, yeah, it's the stars, I've seen it. You're going to go, wow, there's a red giant. Gee, this is a planetary nebula. Gosh,
Right.
look, new stars are being born here. And you're going to, everything from planets, nebulae, galaxies, constellations, coordinates, double stars, all more than 50 activities in here. And they're kind of adjusted by difficulty level, and they get more action-packed as you go along. But it's really designed. You go through the whole book. And you're going to be a very experienced astronomer. It's also broken down into spring, winter, summer, fall activities, because as we know, the sky changes every couple of months. We get new constellations visible. So this will give you, I think there's enough material in here for years of enjoyment and learning and excitement out in the dark. So anyway, I hope you'll pick up a copy. I hope you'll leave a review. And as always, if you have questions, if you read the book and say, what the heck, Doc? You can contact me at Astronomy for Educators. Live on the show, absolutely, right. Or at astronomyforeducators@gmail.com. So this, I am so excited. I look through this and I'm looking at all the pictures and I'm like, gosh, did I do all that? Because it's just beautifully produced. The people at Springer did a lovely, lovely job.
They did a very nice job.
And
I mean, the illustrations
Springer is a
look
worldwide.
good.
Yeah, I know we have a worldwide audience. Springer is a worldwide publisher. So it doesn't matter. It's on Amazon, but if you don't have access to Amazon, you should be able to go to any good bookseller and say, oh, there's a title on Springer that I would like to order, and they should be able to get it for you. Just very thrilled. And for our How Do You Know audience, this really is for you. It's for you folks. And I appreciate your support and coming to the show every week so much. Can't tell you. So great. And we'll leave that there. Boom. And we'll go on to this week's exciting topic. We usually open up, Scott, with a little introductory, and then we get to our main topic. And this week I'm going to do it a little bit different. We got a question from one of our viewers, Pekka.
Okay.
And he was asking me about photons. And he said, hey, Doc, about photons, how can they continue to glow after billions of years? Where does the energy come from? And if photons don't weigh anything, in fact, how are they affected by gravity? And there's a number of answers to that. Let's take the first part first. The photon actually is the energy. So when we say, how does it carry the energy? It is the energy. And when that photon is emitted from a distant star, the surface of a planet or moon doesn't matter. That photon is emitted and that energy is on its way to you. And when the energy reaches your camera, your retina, your eyepiece in a telescope or binocular, then that energy is delivered to your biological retina or to the mechanical retina of a camera's sensor array. And that energy is then delivered to your sensor array, and that's how we see. The other answer about gravity is a little deeper. But remember, since photons carry energy, they must have a mass equivalent. It's common to discuss them as a massless particle. However, that's not quite true. Everything that carries energy has mass. Remember, E equals mc squared. C is an outrageous number. It's 300 million squared. There's a scientific prefix for that. It's called LOTSA.
LOTSA.
Don't look that up in a textbook. You won't find it. I'm kidding. But yeah, 300 million meters per second. 300 million squared is a gigantic number. And when we are trying to find the mass, we have to take the energy of a photon, which is very tiny, and then we have to divide it by 300 million squared. And so the mass is effectively zero, but not quite. And the most concise answer I can give you, Pekka, comes from John Wheeler, famous American physicist who was a student of Einstein. And Wheeler said, mass tells space-time how to curve, and space-time tells mass how to move. And so when particles containing mass of any of the tiniest amount go through the universe, they must follow the local curvature of space-time. And in this case, any planet, star, warps space-time in towards itself, and the photons follow that line of space-time. The easiest way to think of it, again, this comes from Dr. Wheeler. If you think of an ant crawling across the surface of an apple, and the ant says to himself, I'm going to walk in a straight line until I find the end of this apple. Well, we know, he won't ever find the end of the apple, because even walking in a perfectly straight line, he follows the curvature around the equator of the apple or up into the dimple where the stem is. And he's not, his local experience, I'm walking straight on a flat surface. But we know that in the much larger sense, the surface actually is curved, and so it will curve his pathway. Same way, if you circumnavigate the globe, you can start out, lock your car or boat or plane in a straight line and keep going. You'll eventually circumnavigate, even though you haven't turned right or left at any time, because the surface we're driving or flying over is curved in itself. And because space-time is curved, light follows that. I just finished a brilliant book, No Shadow of a Doubt, by my colleague Daniel Kennefick, who is a physicist at the University of Arkansas. And his book, No Shadow of a Doubt, talks about the 1919 eclipse and how Eddington and Dyson set out to prove Einstein was right, that space was curved, that relativity was the bomb. It's a brilliant book, and I enjoyed it very much. And that goes into much more detail if you're wanting to up your game a little bit. It's a good read, very readable. Reads like a detective novel. It's great stuff.
Right.
So there you go, Becca. I'm hoping that.
Yeah, at Yerkes Observatory, they still have the glass plates from the reenactment of that experiment from 1950 or something like that. And there was a big there was a controversy of whether or not because they went to two different places. One group went to an island, okay. Another one was in Brazil, right? And
That's the 1919 eclipse, Sobral, Brazil, and I'm probably slaughtering that name. Excuse me if you're a Portuguese speaker. And then there was the island of Principe, and it's now its own country, and it has a hyphenated name, and it's Principe Tobago something. My geography skills are just anyway. Yeah, and I actually there's a teacher there in one of the local schools who uses my book Astronomy for Educators, and yes, his place was the site of the 1919 eclipse, and Eddington was on the island of Principe off of Africa, off of West Africa, and it's out there in the Atlantic. And yeah, that was beautiful. Pekka has a question. He says, can we learn from photons energy to be able to use the kind of energy on our own? Well, yeah, absolutely. We use it's light energy, Pekka. It's photonic energy, and we use it all the time. We use it anytime we have a marvelous cell phone with our camera here. We turn our camera and go, oh, click, I'm going to take a picture. You're using that photonic energy to record an image. We use it biologically. It gives us our power of vision and all solar power, solar arrays. And whether you're talking a photovoltaic array, it's like a panel on your roof that converts sunlight directly to electricity, or if you're talking about some of the solar thermal plants where they actually have mirrors that track the sun and they reflect the light up to a tower and they boil water to produce steam to turn a turbine. Any of those are excellent examples of the use of light energy. So there we go. Let's jump into our primary topic for today, understanding planetary nebula. And this is really cool because there's a national world event tonight. President Joe Biden is going to release the very first full-color image from James Webb Space Telescope, the JWST. and NASA had scheduled an event to release these images tomorrow, but President Biden said dibs, and he's decided to go ahead and release that tonight. The last time an American president did anything like this is 1992, and it was Bill Clinton who did a national event because of the Martian meteorite, the Allen Hills meteorite with the little microfossils. And that has been mired in controversy for the last 30 years. But I'm thinking the Webb will be less controversial than the Mars meteorite. But it'll be exciting to see this image. And I applied to NASA. I'm sure tens of thousands of people applied for a press pass to go to the event in I think it's Bethany, Pennsylvania. Anyway, I applied. I didn't get picked. Anyway, but so I'm here with you, and Scott's posting a link. And the link is
it's on nasa.gov/multimedia on NASA TV, and I'll post it again. But it's not going to broadcast until 5:30 Eastern, which means that we got 10 minutes before it does broadcast.
Yeah, and our friend Pekka is starting to go deep into quantum physics with me. So I'm I'm not going to do. Maybe we'll do that in another program. Maybe not. But Pekka, I'd be happy to chat with you about these, maybe on the phone or on email. Anyway, there's a link. Oh, good. Scott posted that. Let's talk about Planetary Nebula. The very first thing to know, of course, because, hello, it's astronomy and we're in ancient science, planetary nebula have nothing to do with planets. And you're like, but why? It all goes back to William Herschel and his discovery of the planet we now know as Uranus, or if you're a sixth grade boy, Uranus. Anyway, and he originally wanted to call it George. Herschel wanted to call it George. Why? King George III, his patron, had given him the money to build the telescope, and he says, oh, I'm dedicating this to my patron, which was not uncommon in the day. Galileo did it. He called it the moons of Jupiter, the Medicean moons. And everybody said no, they didn't like that, especially the French at the time. And so for a while, they were calling it the planet Herschel. And then when Leverrier discovered Neptune, they were, for about 50 years, the planets were known on star charts as Herschel and Leverrier. But international astronomers said, let's stick to the naming convention. And so today we have Uranus and Neptune. And so where's the connection, Doc? Well, this is the very first new planet discovered in human history. Throughout history, we've known of the classic planets, Mercury, Venus, Mars, Jupiter, Saturn. Copernicus came across and said, Earth's one too. So, but until that time, 1781, no one had found another planet. And Herschel discovered Uranus. And after he did, a huge worldwide frenzy, both amateur and professional, because at this time, it's kind of like the arms race and the space race. Countries are competing to discover scientific novelties for prestige and bragging rights, and our scientific establishment is the best in the world. This all kind of, chest thumping reasons. But once a new planet was discovered, lots of people said, wow, that's awesome. I want to see if I can find one too. And people kept saying, ooh, I found one, I found one, I found one. And when the more professional mathematical astronomers came around and they said, well, send us your discovery, give us a location in the sky. And it turned out that all of these new discoveries, unlike planets, they weren't moving. Planets have a number of things that distinguish them. First of all, they move. The outer planets pretty slowly, but they do move noticeably. And if you can track them, these new objects didn't move at all. The second thing that planets do, of course, is they're distinguished as a disk in an eyepiece. When you look at Saturn, Jupiter, Uranus, Neptune, Venus, Mars, you see a disk. You're like, ooh, It's not a dot. It's not a point of light like a star. It's a disk. And these things seem to be disk-like. Nobody could quite get a sharp image on them, but they said, no. They're absolutely not a point of light. They're an extended object. And so the mathematical people said, but they're not in the same plane as all the other planets. They're not orbiting in the flat plane that all the planets orbit in, which makes sure it says, is this not a planet? No, but it makes it less likely. The idea that all your planets are on a plane and here's this other planet tilted off at 30, 40, 50, 60 degrees or more, it's not impossible. And we've since found solar systems like that. But at the time, people said, but the mystery persisted for a long time as to what these objects really were. And as I say, as the months and years went on, people would make these discoveries, and they were legit discoveries. They were finding legit objects. And they were saying, gosh, we've found this object, and is it a planet? Can I claim discovery? No, it's a nebula. Well, bully for me. How many of us would not love to discover a new nebula or meteor shower or something like that? We all would. And the astronomical community, the professional community of physicists and astronomers worldwide came to the conclusion within, over a few years that these objects were all way outside the solar system. They were much farther away. And after Herschel discovers Uranus in 1781, it's 60 years, 6 decades until Neptune was discovered. And that's another, that'd be worth a whole how do you know on its own. Because Neptune's the only planet discovered by committee, and it's a fascinating story. And it's amazing. So, but by the time the next planet was discovered, the name Planetary Nebula kind of stuck, and that name has evolved over time. But that name kind of stuck with us, as often happens in astronomy. And we've talked about this many times before. We had a How Do You Know show where I showed this great big stack of astronomy textbook. And I said, hey, guess what? None of these have a definition for planet or moon in their glossary. And people were like, no, that can't be right. And I had people who were going and looking, you're right, it's not there. And it's kind of like the old joke. Somebody says, did you know gullible's not in the dictionary? Yeah, and you go, well, yes, it is. Well, I said, oh, did you know moon and planet aren't in the glossary? And nobody believed me. And it's because the name and the concept is so ancient that our understanding of it has completely revolutionized itself several times over the millennia. And we just keep these historically comfortable names. So you can think of these names like planet, moon, planetary nebula. They're like mom's tuna casserole. It's comfort food. It's not necessarily good for you. And you go, well, is it tuna casserole? Well, it's not real tuna. It's not made in a casserole dish. It's made in a frying pan. But, you know, that's what we call it because mom likes it. And we just have these names that we're comfortable with after hundreds, thousands of years sometimes. And they simply stick with us. So basically, all right, it's not a planet. What is it? And of course, how do you know? Well, if we talk about a planetary nebula, it's actually the remains of a dead star. And it's the remains of a dead star, very much like our sun. You take a common dwarf star, somewhere between, and again, here, guys, different scientific theories and numerical models differ on this. So somewhere between anywhere from 1 solar mass to 5, maybe 8, maybe 10 solar masses. And when these stars get old, let's take our sun for an example. Our star is about halfway through its life cycle, about 5 billion years old. It'll last about another 5. And when you say it will last, well, what do you mean? Well, at some point, stars die. How do stars die? Kind of like campfires die. They run out of fuel. And so if we think of a star as a cozy little campfire around which are home planets are gathered. What does it burn? Not wood, certainly. It's burning hydrogen, as we know, and burning, another one of those sloppy ancient terms. We know that hydrogen is really fusing into helium. So two single protons, hydrogen atoms, are fusing together to make a single helium atom. And again, I'm really simplifying the process. But nevertheless, once the hydrogen fuses to helium, it releases a lot of energy. And we're talking heat, gamma rays, neutrino, ultraviolet, visible light. And this energy starts out in the core of the star, and as it goes out through the star, that energy is emitted, and then it's reabsorbed, and then it's emitted again. You can kind of think of this process of a photon of energy going from the stellar core to the surface. It's really slow. It takes about 100,000 years for a single photon of energy to make its way from that fusion event in the stellar core all the way out to the surface and then be released as either ultraviolet, X-ray, gamma, visible light, whatever. And you're like, oh my God, the sun's not that big. Doesn't light travel at 3 million meters per second? Why does it take that long? It's because of the emit and absorb. So the photons are essentially passed off. They're emitted from this atom, and then bing, they strike something else and it's absorbed, and then they're re-emitted and reabsorbed. And I told my students, imagine if we took a school gymnasium. Let's say we packed a school gymnasium full. We put 1,000 people on the gym floor. And then we turned out the lights. Absolute blackness. And in one corner of the gym, we give somebody a tennis ball. And we said, okay, reach out until you bump somebody and hand the tennis ball out. And every time you get the tennis ball, you have to spin around 3 times and then hand it off to somebody. And you can see, how long would it take the tennis ball to get from one corner of the gym to the other? You might be old and gray before this happens. Because after a while, people are confused. And the direction a photon strikes an atom and then the direction that it leaves have no connection. It's completely random. And so this random handoff, by process of elimination, the photons do eventually make it to the surface of the star, and they are emitted. But what happens? Eventually the helium runs out, or the hydrogen runs out. There's no more hydrogen. That's a bad day, Scott. When your star runs out of hydrogen, it's a bad day. Yeah. As the old joke goes, put your head between your knees and kiss your bottom goodbye. And what happens with no more fuel, you realize it's the fusion explosion that inflates the sun to the size that it is. The energy of the output of the sun is very consistent, and the gravitational force trying to collapse the star is very consistent. And so we see the sun as having a precisely defined diameter. But essentially, it's kind of like if you took a balloon and you took a pin and you put dozens of holes in it and you blow it up. Can I keep blowing up the balloon fast enough to keep it at a fixed diameter? Well, yes, I suppose you could, but you have to be pumping air in at the same rate that air is going out. So we realized that, the sun has to be producing energy just as fast as it's emitting energy into the cosmos in order to stay the same size. It's a very robust and stable process until the day you run out of fuel. Because then, as happens ultimately everywhere, gravity wins. Once gravity wins, the hydrogen...
Is that a quick process when it gets to the...
It is a quick process. Seconds?
Seconds.
People...
Okay.
So
our sun, when it runs out of hydrogen fuel, it's going to be seconds until it becomes red giant.
The red giant? No, the red giant process, but the actual collapse where the star shrinks, very, very fast.
Yeah.
The gravitational acceleration, the sun's gravity on the surface, could you stand there, is about 30 gravities. So a 100 pound or 100 Newton weight, remember guys, kilos are mass, not weight, If we're talking about a 100-pound weight, it weighs 3,000 pounds. So a 100-pound weight, a 50-kilogram object on the surface of the sun would effectively weigh the same as a 1.5 metric ton mass on Earth. It's outrageous, and this gravitational collapses the sun. Well, guess what? As it's collapsing, the pressure in the core increases. Pressure equals heat. Trust me, that's true. It's like another whole program we could have. But pressure equals heat. And what happens to pressure, the temperature of the core, which was a balmy, pleasant 10 million Celsius, during this collapse, the core temperature rises to over 100 million Celsius.
Yikes.
So the pressure goes up by a factor of 10. And when it hits around 100 million, it's now hot enough that we can fuse helium and make things like carbon, oxygen, nitrogen. There are different cycles and processes here. Well, because the hydrogen is, forgive me, burning at 10 times the temperature, remember it's largely heat energy that expands the sun, this new improved 10 times hotter stellar core inflates the layers of gas and plasma around the stellar core enormously.
Yeah.
Our pleasant, comfortable, million-mile wide sun will inflate at least to fill the orbit of the Earth and possibly reach out towards Mars. It's likely that Earth, which will continue to be a solid body, will be orbiting inside the red giant's envelope. Don't worry about that. You can think of a red giant as a red-hot vacuum. Why? The star hasn't gained any mass. When it's burned up its hydrogen and it has started helium, it's still essentially a one solar mass object, but now instead of putting it in a one stellar diameter package, we're now expanding it to fill an orbit that's about 1 AU. That's its new radius. Not 500,000 kilometers. It's now, oh my God, it's 1 AU is the new radius, and you're spreading that material over that huge volume. So a red giant is essentially, certainly its outer layers, better vacuum than you can pull in most laboratories on Earth. So it's a red hot vacuum. The Earth could happily continue to circle the core. Of course, it's 3,000 Kelvin, so it's going to boil away all the oceans and the volatiles. And yes, life goodbye. The life on the planets are dead. The inner planets certainly. And this process of burning helium continues. But again, the sun is a great recycler. But again, at some point, the helium fuel is exhausted. And general rule, and if you've done any kind of a campfire, camping out, you know, the hotter you make the fire, the faster your fuel burns, right? Oh, let's make a big fire. Oh no, we're going to use all the wood. Let's feed it modestly, and it has to go all night. Well, this much hotter core burns up the helium fuel much faster, and it reaches a day when the helium fuel is exhausted. And then you have, depending on mass, and remember that during this whole red giant phase, there's a huge stellar wind. The star is essentially blowing off plasma, gas, dust, all sorts of things. The star is essentially losing weight, shedding mass. Depends on how heavy the stellar core is when this process is done. But let's just stick to small dwarf stars like our sun. Once the helium is done, then the star collapses again, and this really is the end life state. And we have what we call a nova. This is not a supernova. Supernovas are much, much larger and more energetic. A supernova will kill you from 50 light years away. A nova, not so much. And it would be cool to see something like a star, Barnard star, Proxima, something within, say, 50 light years, have a standard nova. That would be awesome. And it would be a light show in the sky for centuries, millennia to come. But what happens with these objects is essentially you can think of it as a bounce. This material runs in and there's one more bang, and that bang blasts off all the outer layers. This, friends, is how stars, number one, produced by fusion, things that we are familiar with like carbon, oxygen, nitrogen, phosphorus, all the basic elements of life. And when the second time the collapse, and then boom, we get this bang. And the bang, the second time, the nova explosion is big enough to blast material out into interstellar space. So what you're essentially doing is you're taking all these shells of very thin, very vacuous shells of gas and dust, and we're blasting them off into outer space. What's left after that at the core now becomes a white dwarf. This is not a star. I know. It's sometimes referred to in the media and the popular press and science press as a white dwarf star. It's not a star. Oh, but I can see it in my telescope. It looks like a star. It's a bright white point. No, it's not a star. It's dead. Stars are alive. Stars are fusing hydrogen, helium, and other fancy things in their core, and they're producing energy. A white dwarf produces nothing. Its life is over.
Off, right?
It's just cooling off. But here's the thing, Scott, and it's fascinating to think about. An object in space can only radiate energy from its surface. And you're like, yeah, okay. So you think of a star and you think, oh, all the light and heat comes off of its surface, right? Well, sure.
Right.
You can think of that surface as a window. Well, what we've done with the white dwarf is we've taken a red giant, 2 AU in diameter, and we've compressed it down into an object the size of the Earth, say 10,000 kilometers.
Okay.
Well, we've taken this thing and we're talking about what, 300 million kilometers in diameter, right? And we've now compressed it to 10,000 kilometers in diameter. What we've also done is we've shrunk the surface area by more than 1 billion. So since that object can only radiate out through the surface is now really small. That means we've compressed all that energy into a small spot. The white dwarf object becomes very, very hot, and it cools very, very slowly. Imagine if you had
going on.
Yeah, imagine if you took a pot of very hot soup or boiling coffee and put it in a really well insulated container that would let out virtually no heat, and then you just took a drill and you drilled a tiny hole through the top of your insulated container and said, oh, now it'll cool off. Well, yeah, it's going to take a while, champ. And that's exactly the situation. But these objects, these white dwarfs, are so hot that they're not only radiating in visible light, but in infrared and X-ray and gamma and all sorts of frequencies. And what's happening is now you have these shells of gas which are expanding. And when we look at this, we know what happens now, because we all have this technology. I'm sitting underneath some of this technology here in the studio. We have lights. Probably most of you have compact fluorescents in your home. You may have fluorescent tube fixtures in your place of business. And how do these work? We bombard very thin gases, and they give off radiation, and the radiation makes the phosphorus in them fluoresce or glow. If you've ever seen a black light and you've had a glowing poster or a glowing mineral,
right.
Scorpions are also fluorescent as well, oddly enough. Although I've never felt the desire to go out in the desert with a black light and find one. They are fluorescent. And what happens is an object gets struck with a photon, and then it emits a different photon, often at a different frequency. And again, there's good quantum mechanical reasons for that. But what's happening here is all this hard radiation is flying out from the white dwarf, and it's slamming into this spherical, expanding bubble of gas and dust. And when it does, it energizes that gas and causes it to glow. And because the brightness of the glow depends on the density of the gas.
Mm-hmm.
And also, the brightness of the glow depends on the amount of surface area. Remember what we said about the surface area of a regular star and a white dwarf? Well, guess what? This shell of gas that we're talking about for a planetary nebula has a much, much larger, enormous surface area compared to the white dwarf. And it's all glowing. Well, that's great. So this high energy causes fluorescence is the technical term. And then basically what it amounts to is we knock an electron off and then it comes back and causes a glow. If you've ever played with one of these toys that do this, Newton's cradle, sometimes called, the little ball cradle, it's just like that. Oh, comes in, gives it some energy, kicks it out this side, brings it back, and off it goes. But it's a much more random omnidirectional process. So we've got basically the ring nebula and all these planetary nebula are fluorescent lights. There's these little fluorescent night lights up in the sky just for you. And remember, these shells of gas are not static. When the nova goes off, the shells of gas and dust leave the star, and they're traveling at thousands, maybe tens of thousands of kilometers per hour, enormous velocities. And so over time, these things get bigger, but as they get bigger, they also thin out. Remember, there's only a certain amount of matter, gas, plasma, dust. And as it expands into a larger and larger volume, it's like spreading your butter over too much bread. The density goes down, it becomes really, really thin and rarefied. And because it becomes very thin, as planetary nebula age and become older, they become more diffuse, less bright, their magnitude diminishes, and eventually they will fade away and disappear. That's what we see. But we also have to remember what's happening. These gases that we see glowing in the night, they contain hydrogen, helium, lithium, neon, argon, carbon, oxygen, nitrogen. They contain all of these lower mass elements from the periodic table. And what's happening? This nova explosion has cast them out. Effectively, fertilizer? I know, that's a terrible term. Can't come up, but it is, isn't it?
Term, though. I mean, it's
a good analogy.
Universe, right?
Right. And so we see, and it's interesting, and I will tell you, one of the beautiful, I don't know what photo Mr. Biden is going to release tonight, but I know one of the photos NASA is releasing tomorrow is the Southern Ring Nebula, which is a companion to our Northern Ring Nebula. And this nebula that they're releasing, it's not a perfect ring. And I had somebody look at it. Oh, I looked up a picture. Why isn't it round? Well, the answer to that is simply that space isn't empty. Whenever throughout the 13 billion year history of the universe, stars have been dying, exploding, and casting enormous amounts of gas, dust, and cold neutral atoms out into space, clouds of them.
Right.
I'm sure most everybody on this show has looked at the Orion Nebula at one point. Big clouds of gas and dust containing all the elements, basically all the elements. Well, where did those elements come from? They came from explosions and blasting out planetary nebula, and the cloud runs in. And if you think of smoke from a fire that hits a bank of fog, and, well, will the two of them pass through each other? No. If you have a bank of fog that's here stationary and the smoke comes along, what's going to happen? The smoke is going to slow down where it hits. It may wrap around. It's going to change shape. It's going to be dynamic. It's a flow thing. Think about looking at the side of a glass of water and dropping a drop of food coloring in. it goes and it hits and it moves and it changes shape. It's a very turbulent and dynamic process. So the older these nebula become, the less spherical they are, the thinner they are, the dimmer they are, the less brightly they shine. But they're also casting, I don't know if casting your pearls before swine is the right idea, but it's the ultimate recycling program, right? All of these molecules will eventually be used up in a new solar system. So the carbon, the oxygen, the silicon, the nitrogen, they're what made us. There were stars billions of years ago who lived, died, and went boom. And when they did, they blasted out shells of gas and plasma, clouds of dust, and like I said, the whole alphabet soup of elements from your periodic table floating out in space. And when these come together, they hit a new cloud, they enrich it just enough. Oh, I'm just heavy enough now. My self-gravity can start compacting that cloud, and eventually you get a new star. And the star, once it's born, it's surrounded with its own shell of gas and dust. And the rotation flattens this sphere into a disk, and voila, planets form. We talked about autogenesis. And in this program, we talked about autogenesis, specifically autobiogenesis with the formation of life on planets. We've talked about this idea of self-assembly. Well, yes, these elements that are in the ring of the southern ring or the northern ring in the constellation Lyra, these atoms, if you will, they will become part of a star system. Every part of me and you, sitting here, listening to this program, thinking, living our daily lives, and Carl Sagan said this, you are made of star stuff. All the atoms in us were forged in a star and cast out willy-nilly into space, and later became part of a planetary system and eventually part of you. And if you need some carbon molecules right now, carbohydrates. I just consumed carbon, oxygen, and God knows what all. But basically, every atom in my soft drink was forged in a star.
That's true.
Every atom in it. And it's now going to be part of me. And some of those carbon atoms are likely to walk around with me for some number of years yet, I hope. And our bodies are constantly taking in things and eliminating things. But all that is us, all of our physical body and that is here, all of the atoms went through this process. All of them. Whether it was a ring nebula or a planetary nebula or not, we don't know. Could have been a supernova, could have been lots of things. But all of your atoms went through this process to become part of a new planetary system and ultimately part of you. So it's a really cool, and we talk about non-spherical. The very first planetary nebula discovered was the Dumbbell Nebula, which many of our friends here are familiar with. The dumbbell is it's shaped like a dumbbell. People say, well, why is it that shape? Well, it's just, why is a cloud the way it is? Why is a cloud the way it is? It's interacting with wind and different densities, humidities up in the atmosphere. We can't see them, but we see the cloud's shape change as it moves along, and we know these processes are going on. And the dumbbell was discovered by Messier. No one knew it was. No one classified it as a planetary nebula for, many decades, if not a century or more later. So that was really fascinating. The other question I got asked this morning in my interview with Mr. Pauka is, well, why do you think NASA picked the Southern Ring Nebula rather than the more famous M57 ring nebula that we are all familiar with here in the Northern Hemisphere? And I think there's nobody, first of all, nobody from NASA's Webb telescope team got on the phone and said, hey, Dr. Barth, what target should we point Webb at? Oversight on their part, obviously. I'm sure that'll improve as the years go by. But I think they had a number of reasons. First of all, Webb, because it's infrared, is designed to peer through clouds of dust and plasma that block the vision of visible light telescopes like Hubble and, of course, ground telescopes like yours and mine. Well, Webb looks in the infrared. Why? Because instead of being blocked by a cloud of dust, the longer infrared wavelengths pass right through. And these are inherently dusty objects. They're also very well understood. And when we compare this Southern Ring Nebula with the more famous M57 in the Northern Hemisphere, we find out that the Southern Ring is both younger and closer. And so we've traded in the Ring Nebula for a younger model, guys. What we're looking at, the Ring Nebula that we know of, M57, is about 2,500 light years away, whereas the Southern Ring Nebula is only 2,000 light years away. It's 20% closer. And when we compare the diameter, the Southern Ring Nebula is just half a light year wide. Just. Don't you like that when we talk about astronomy? We can talk about just half a light year, like, oh, down the block. So it's just half a light year wide, whereas the M57 Ring Nebula is 1.3 light year wide. So we've got something which is younger and closer. And because Webb is supposed to look through dust, it's also denser. So it has three things that will serve as an excellent test for Webb. I also think probably NASA, if I had to guess, I'm betting NASA will pick various targets from around the sky. They're not going to be so foolish as just say, let's only look at things that people in the Northern Hemisphere can see. They're not going to do that. And so I think they decided that this was an excellent object in the Southern Hemisphere, and that will be excellent. This is going to be so exciting. I hope all of you, if you can't tune in tonight to Mr. Biden's announcement of the first image, keep in mind that tomorrow, NASA on NASA TV, and it's a world event. It's going to be on all the media outlets. NASA will be revealing the first 4 fully processed, full-color images from the James Webb Space Telescope, and that's their major announcement, and that'll be tomorrow. So I'm hoping that members of our audience are going to tune in or look this up on YouTube. You know it's going, I can't watch why the event is live, okie doke, but you know it's going to be on YouTube, it's going to be on Facebook, it's going to be everywhere. So I hope you'll take a look at it. I'm very excited. And when you see the picture of the Southern Ring Nebula tomorrow, then you're going to say, I know what that is. It's a dead star. And somebody will look at you and say, well, how do you know that? Because you're here every week, you'll be able to answer. Because this has been How Do You Know? And I hope you've enjoyed this week's program. And I hope if you have a chance, you'll go ahead and pick up a copy of Star Mentor. It's on Amazon.com right now and Springer.com. And Springer is a global company. So no matter where you live, your local bookseller should be able to get you a copy. And I hope you'll enjoy it. Like I said, there's a lot in here for How Do You Know fans. There's some in there that you'll find familiar, but there's an awful lot that's new, different, exciting. And let's go places together. It'll be exciting. So do we have good questions this week, Scott? Do we have fun questions? I always love my Q&A time.
Let's see what we had here. Pekka's got great questions. Here's another one. Can Dr. Barth explain closer the difference on weight and mass, and what has weight and what has mass?
Certainly. Mass is the amount of matter. So if I have a PMC8 coffee cup here. So if I take a look, this is a solid object. It has molecules, it has atoms, it has matter. The amount of matter here is its mass. Now, if I take this coffee cup to the moon or to Jupiter or interstellar space, it still has the same amount of atoms and molecules, and basically it's a solid, the same arrangement. Its mass, its number of atoms will not change. Weight is different. Weight is how hard a gravitational field pulls on you. Let's just say, I'm weighing this, let's just say this cup weighs 0.2 pounds, or if you prefer, 25 newtons. I know most of the world audience is used to talking about mass and not weight, but the metric unit for weight is the Newton. It's a unit of force. Weight is a force. How hard is gravity pulling down, or otherwise, how much force do I have to put underneath to keep this object stationary? Because if I cease to apply force, of course, it falls. So if I go to another planet, if I go to the moon, on Earth I weigh, let's just, for easy numbers, say 180 pounds. I'm more svelte than that, but it's an easy math number. If I go to the moon's gravity is 1/6. So if I take 18 and divide by 6, I'll get 3. And so on the moon, I would weigh 30 pounds. So my 180-pound weight, and I think that would make me something like 80 kilos. On the moon, I would still be 80 kilos, but my weight would change from 180 pounds to 30 pounds, which meant that since I haven't lost any strength, if I could make a 5-foot high jump, let's say a 1-meter high jump here on Earth, I could jump a 6-meter high jump on the moon. On the other hand, if I went to Jupiter, I know, no solid surface, go with me here. Jupiter's surface gravity is about 4 Earth gravities. So instead of weighing 30 pounds, I would now weigh 180 times 4, which would be, 760 pounds? I couldn't move. Likely my heart would collapse and not be able to pump blood. It would be a crushing, it would be a crushing gravity. I know there are people who are young and fit and can take 4 gravities. I'm not sure I could at my age. But yeah, the force on you changes. That's the weight. But the number of molecules and atoms in me does not. That's my mass.
There you go.
There you are.
There you go. I don't think so. I think that's it. People wanted to thank you for a great show. Pekka says that he always learns much when he watches How Do You Know? And
thank you so much, Pekka.
Yeah. And so I think that might conclude our program. And
Wrapping it up.
Joe Biden, if you're watching, thank you for tuning in. And have a great James Webb Space Telescope program. So
absolutely, and I'm sure we'll be chatting about that on next week's How Do You Know? But in any case, we'll see you here next week, Monday, same time, same place, and love you all. Thank you so much for your the audience support here. Scott is just terrific, and can't tell you how I appreciate it. Matter of fact, I got to tell you guys, the reason I got contacted by NPR is because of the Astronomy for Educators, which you guys have known and promoted and shared with your friends. So my success is your success, and can't say enough about how great the audience is on How Do You Know and Explore Alliance.
Right. Also, I want to let everybody know that tomorrow we will have the 99th Global Star Party that will start at 6 p.m. Central, 7 p.m. Eastern. So we are excited to bring it back after being gone for a couple of weeks, as I made my trip out to California. And then the following weekend, or the following Tuesday, will be the 100th program of the Global Star Party. And we have a big lineup of people already.
I'm clearing the decks, Scott. I'm going to be on the 100th.
That's good. That's great.
so many times there's things I want to do, and there's things get crowded out by life and writing, teaching,
sure.
outreach. But I will not miss the 100th Global Star Party. Put me on your guest list. I will absolutely be there, and thrilled to be part of it.
Thank you so much. Thanks, Daniel. All right. And I think that might be the end of our show. As our friend Jack Horkheimer always used to say, keep looking up, and we'll see you tomorrow.
Clear skies, everybody. And there we go.